Okay, exponential functions. This comes from chapter 3 of our pre-calc course, mainly the first and second sections of chapter 3. We're going to work on writing functions in y equals a times b to the x form, inverses of exponential functions, and applications of exponential functions. So let's get started. Writing equations of exponential functions in y equals a times b to the x form is first. So find the equation of the exponential function that passes through the points 2, 36, and 4, 81. Obviously, you can use the graphing calculator to do this. However, I'm going to show you how to do it by hand. So we have y equals a times b to the x. What do we know in that? Well, we know an x and a y value for each. So if I substitute x and y, this is just like Alg B for us, where you learn about solving systems of equations. We end up with 36 equals a times b squared, and then we end up with 81 equals a times b to the fourth. Okay, so we have two equations, all right, and we have two unknown variables, a and b. So we have a few ways to solve that. I'm going to demonstrate the equal values method. So I'm going to get one of these variables by itself, and the variable that I'm choosing is the a because it does not have an exponent. So here I would divide by b squared, so a equals 36 over b squared. And here a would equal 81 over b to the fourth. Okay. Now that I have a by itself for both of these, I can let these two equations equal one another. So 36 over b squared equals 81 over b to the fourth. Cross multiply, and you end up with 81 b squared equaling 36 b to the fourth. Now if I have two b's on this side, 4 on this side, these two will cancel out, and two of these will cancel out. So 81 is going to equal 36 b squared. Divide by 36. Okay, 81 over 36 reduces to 9/4 equaling b squared. And if I take the square root of both sides, b ends up being 3 halves, or 1.5. So now that I have b, okay, I can come back up here, substitute, and find a. So a equals 36 over 3 halves squared. So a is going to equal 36 divided by 9/4. But instead of dividing by a fraction, I'm going to multiply by its reciprocal. So a is going to equal 36 times 4/9. Well, the 9 and the 36 reduce to 1 and 4. 4 times 4 is 16, so a equals 16. Now, after all of that work, do not forget what the original problem asked us to do. The original problem asked us to find the the equation for the exponential function. So, in the end, y equals 16 times 3 halves to the x power. That's your final answer. Next problem dealing with exponential functions, y equals a times b to the x, is to rewrite the given equation in y equals a times b to the x form. So we're looking for a number a, a multiplier b, and just the x as the exponent. Here we do not have that. We have 2x plus 2 as the exponent. So what we're going to do here is we're going to use our properties of exponents, but we're going to use them in reverse. Instead of combining things with similar bases, we're going to separate. Okay, so we have 4 times 3 to the 2x times 3 squared. Just like if you would have had this before with the same base, you would have been told to add the exponents. We separate them here. The reason we do that is because we know what 3 squared is. 3 squared is 9. So we end up with 4, 3 to the 2x times 9. And because of associative property, the 4, or commutative property, 4 times 9 is 36 times 3 to the 2x. Again, we're almost there, but we still have this 2x and not just an x. So we can use our power property for exponents and say 36 times 3 squared to the x power. And the reason we do that is because we know what 3 squared is. 3 squared is 9. So in the end, if we rewrite this equation, we end up with y equaling 36 times 9 to the x power. And these two equations would be equivalent. inverses and exponential functions. So find the inverse of the given function. Is the inverse a function? So we have f of x equals 5x over 2x minus 3. To find the inverse, we're going to first switch x and y. So x is going to equal 5y over 2y minus 3. That's the easiest way, I think, to find an inverse. And from here, we resolve for y. So we multiply both sides by 2y minus 3. So we end up with 2yx minus 3x equaling 5y. Okay, if we're solving for y, we want to get all of our y's on the same side. The reason we did this is because we didn't want the fraction. Okay, so let's get our y's on the same side. So I'll subtract 2yx from both sides. So I end up with negative 3x equaling 5y minus 2yx. Now that I have my y's on the same side, I still have two of them. One here, one here. So because both of these terms have a y in common, that allows me to factor a y out, which leaves me with 5 minus 2x equaling negative 3x. Now to get y by itself, I simply divide by this quantity, 5 minus 2x. Okay, and I end up with the inverse of f of x equaling negative 3x over 5 minus 2x. Now, depending on your steps in here, all right, you may have gotten a little bit different looking result. You may have gotten 3x over 2x minus 5, both of which are equivalent. Find the inverse of the exponential function. Now, this is a little trickier, but we're still going to start the same. Okay, we're going to switch x and y, so we end up with x equaling 4 times 3 to the y minus 2 minus 1. And resolve for y. Well, y is all the way up here in the exponent, so we can't deal with that yet. Let's move the 1 over. So x plus 1 equals 4 times 3 to the y minus 2. And then we're going to divide by 4. So x plus 1 over 4 equals 3 to the y minus 2. Now that we're on the y here, now that we're in the exponent, the only way to get a variable out of the exponent is to convert this exponential function to a logarithmic function. Okay? So when we do that, we're going to end up with y minus 2 equaling log base 3 of x plus 1 over 4. There's a separate lesson on converting these that you can feel free to view as necessary. And then last, to get the inverse of y, we're going to add 2 to both sides. So our inverse function ends up being the log base 3 of x plus 1 over 4 plus 2. Okay. Applications of exponential functions. So here's a few word problems that may appear on the test. Population of a certain country was 2,345,235 in 1985 and 3.45-ish million in 1995. Assuming the growth is exponential, find a formula to model the population T years after 1985. So we're going to use 1985 as year 0. Okay. Use the formula to find the time required for the population to double. So if 1985 is year 0, and we know that this was the population, that means that's our initial value. Okay? So if we go ahead and we look at y equals a times b to the x, and we fill in what we know, we just said that in year 0, this is a is going to be 2,345,235 times b to the x. Well, we got to figure out what the b value is. So we're going to use this number and this year, which if 85 is year 0, okay, and then that means 95 is going to be year 9, okay. So, right, 80. What am I thinking? 95 is year 10. Yeah, duh. Okay, so 95 is year 10 with that population. So we plug in for x, we plug in for y, we solve for b. So we have 3,458,377 equals 2,345,235 times b to the 10th. So we divide both sides by 2.345 million or so, and we're going to take the 10th root. So b to the 10th ends up equaling punch that in my calculator there. Sorry, my mental math skills are lacking when we're talking about millions. Okay, so we have 3,458,377 divided by 2,345,235, and we end up with 1.4746 dot dot dot. Then I take the 10th root of that. Okay, and I end up with 1.00396. Okay, so that means the population is growing by 3.96% per year. All right, so my formula ends up being y equals, okay, 2345235 times 1.0396 to the x. Okay, and use the formula to find the time required for the population to double. So in other words, when is 2 going to equal 1.0396 to the x power? And again, this goes back to logarithms. So x is going to equal the log of, well, let me show you the in-betweens here, okay? Instead of doing that, we would take the log of both sides. So the log of 2 equals the log of 1.0396 to the x, okay? Then I use my power law of logarithms to bring that x down in front. And then I'll divide both sides by the log of 1.0396. So x ends up equaling the log of 2 divided by the log of our previous answer, and that ends up being 17.85 years after 1985. Okay. And last, recall the compound interest formula. P times 1 plus R over N to the NT power. Eva has invested $5,000 in account earning 5.4% compounded daily. Ooh, so she will withdraw the money when she has made $2,000 interest. How long will she have to wait? Ooh, $2,000 in interest. That means the total account value is going to be $7,000. So let's discuss what we have here. P is 5,000. All right, A is $2,000 more than that, so 7,000. Okay, R is 5.4% or 0.054, and N is daily. That's 365 days in 1 year. We could get technical and go a fourth. All right, and T is what we're looking for. T is unknown. So we have 7,000 equals 5,000 times 1 plus 0.054 over 365 to the 365 t power. So let's start here. We would first divide by 5,000. All right. So that will give us 7/5 equaling 1 plus 0.054 divided by 365. Plus 1 equals 1. Whoops. So 1 plus this mess here equals 1.0001479 to the 365 t power. And at this point, again, you're going to take the log of both sides. So the log of 7/5 equals the log of this mess to the 365 t power, and then I would use my power law to bring that exponent down. So 365t times the log of the mess, and then I divide both sides by the log of the mess, and then I'm going to divide by 365 at the end. So the log of 7/5 divided by the log of my previous answer ends up being 2274 0.47 equaling 365t. And we divide that by 365, and I find out my time ends up being 6.23. So, how long will she have to wait? She will have to wait 6.23 years until she makes $2,000 in interest, which is very unlikely, by the way. $2,000 in interest in 6 years. And that is it.